Hello guys, Sir DB again here to continue my sample problem. This time I'm using the equilibrium method. So this is a problem on yield line analysis, and in my previous video I showed you how to deal with the usual method in approaching the problem. So we will be solving the same problem using this time the concept of equilibrium method. So to give you a recall of the dimensions, so this is actually, I think, 12, and this is 63. Okay. So this is a 12 by 63. A triangle with fixed support, sorry, it's a simply supported edge here, also a simply supported edge here. And we assume a yield line coming from the vertex C going down here. Okay, and I think also we assume a distance of x from point B to approximately the location of your uh, uh, yield line at the side, the edge or the side A. So I also want to give you the values of m1x and m1y. So this is I think 8 and 10. This is a cube foot per foot unit. And the solution that I showed here is actually discussed on my derivation. So just see the derivation uh, of the equilibrium equations for shear in my previous video. Okay. Okay. So in this particular case, the equilibrium, since it's an equilibrium equation, so all we need to do is to use the equations of equilibrium or the equilibrium equation. So if we take summation of moments at this arbitrary uh, so this arbitrary uh, line AC, which is actually one of the support edge here. So all we need to do is to get the component of whatever uh, uh, forces, no, we have, and the moment arm we, we, we need to get to uh, satisfy this first equilibrium condition that I need. So if I will be isolating this segment of the slab, this part here, let's say slab segment 1, now take summation point AC. So there will be a weight that is concentrated at the center of this triangle. And we know that the center of this triangle is actually passing the point from which we connect the vertex T going perpendicular downwards here. Okay, so this would be W, uh, which is 1/3 this distance here. Okay, so if I know this distance, I just get 1/3 of this. I have the moment arm. Okay, so this 1/3 of T, this is the moment arm of W, and I have 1/2. The base is actually AB, 16 lengths times 12, which is his height, multiplied by W. And I have a shear here, very, very near to D, that will have a, an arm of dB. Of course, this will be counteract the load. And then again, I also have my moment, okay? My moment M and Y coming, okay, from the reinforcement along direction y. So this is simply uh, 10, which is given here. Okay, so 10 times the length, which is x. So this is now the total movement. Okay, m and y times x is this is a cubic foot per foot, then multiplied by x, which is in feet. Then we take, of course, the cosine of that. The cosine of that is actually this one here. Now, so we are actually taking the moments of this direction. Remember, the double arrow means that you put your thumb directed on this, and then the curl of your fingers will dictate your direction. So this is now cosine theta, since this is your angle theta is assumed. So this angle here and this angle here are just the same. So this is just a component which is okay parallel to this one. So this is a 10x cosine theta minus this other one here is 96 sine of theta. Okay, so this is now my equation 1. And similarly for my slab panel 2 or slab BBC, okay, I will get, using the same procedure, I will get my equation. Okay, so again, this is the weight, this is your uh, area, okay, and this is your load, this is your arm. Okay, then we have shear depth times x. I take this as my arbitrary axis of rotation. So this is my arbitrary axis or moment, ABC. And then minus of 96, we have here a 12 times 10, sorry, 8 times 12, which is x kips, because this is in kips foot, and this is m and x times 12. Okay, so this is uh, along the x-axis. Our x-axis is directed here, but our moment is the double arrow is this one. Okay, so this is now along x-axis, but this is about the y-axis. Okay, so please be very careful on that. There's a difference between about and along. So when you say along the x-axis, it will be about the y-axis, and this pertains to mx. If I say about the x-axis and along the y-axis, then this is pertains to mx. Okay? Okay, so I have two equations only, but I have three unknowns to find with the shear force P. Okay, so how do I get the shear force? So this is now the procedure I've done. So please watch my video here on equilibrium. Okay, but I'd like to show you that the final solution will only be, this value here will only be obtained by using the formula mn uh, b cotangent of alpha plus mn. Okay, so this is your q in my video, which is actually equivalent to. So upon getting 10 cotangent alpha and equate it to this uh, equation here, coming from uh, uh, okay, so cotangent alpha is simply 6 over 12. So this will be equated or substituted to uh, 1, okay, and 2 to get a formula for the loop. Okay, so we will have two substitution will create two equations, and solving this simultaneously will give you this value. Okay, so which is the same with that obtained from the first method, which is the virtual mode. Okay, so that's it. Thank you for listening. Have a nice day, and I'll see you on the next. Thank you.